All right, let's get into it. If you've spent any time with C++, you know it's all about keeping your data tucked away safely inside classes. But what happens when you need an outsider to get a special key to that data? Well, today we're going to demystify one of the most powerful and, let's be honest, sometimes confusing features in C++, the friend function.
So here's the game plan. We're going to start with the core problem, why we even need something like this. Then we'll introduce the friend solution and go over the rules of this special relationship. After that, we'll see it in action with two really cool code examples. First summation, then swapping. And finally, we'll have a little debate. Is this a brilliant feature or a major flaw?
Okay, so let's start at the beginning with encapsulation. It's one of the big ideas in object-oriented programming, right? You bundle your data and the functions that work on it into a nice, neat package called a class. And the whole point of the private keyword is to act like a shield, protecting the class's internal information from the outside world.
But that shield creates a really interesting problem. Let's say you have two totally different classes, maybe a manager class and a scientist class, and you need one single function, let's call it calculate_bonuses, that needs to dig into the private salary data of both a manager object and a scientist object. How do you do that? A normal function can't get past the shield, and a function inside the manager class can't see the scientist's private stuff, or vice versa. So what do you do?
Well, this is where C++ gives us a clever little workaround. The solution is to have the classes declare that outside function as a friend. Think of it like giving that function a special all-access backstage pass. It's not part of the band, but it can go anywhere it wants.
So let's get the official definition on the table. A friend function is declared inside a class using the friend keyword. But here's the twist, and this is the most important part. Even though you declare it inside the class, it is not a member of that class. But, and this is a big but, it gets all the privileges of a member with full access to everything private and protected. It's a fascinating paradox.
So why on earth would we need to bend the rules like this? Well, the main reason is exactly the problem we just talked about. You need one function to be shared between multiple classes, and that function needs to access the private guts of both. This is super handy in some very specific cases, especially with operator overloading. When you want to use symbols like the plus sign to add two of your custom objects together. That addition function needs to see the private data of both objects it's adding, and that is a perfect job for a friend function.
Now, you can't just give out this kind of special access without some rules. A friend function behaves very differently from a regular member function, and you've really got to know these differences.
So here are the key things to remember. First, it's not actually in the class's scope. That means you can't call it like myObject.friendFunctionCall. No, that won't work. You just call it like any other normal function. And because it's an outsider, it has to be explicit. It needs to use an object and the dot operator, like myObject.privateData, to get what it needs. A couple other quirks. You can declare it in the public or private section. It makes no difference. And it almost always takes objects as its arguments.
Now, there's a bit of programming etiquette we have to follow. Before a function can be friends with two different classes, we have to properly introduce those classes to the compiler. And we do that with something called a forward declaration.
But why? Why do we need this extra step? Why can't the compiler just look ahead and figure it out on its own?
Well, it's all about how the compiler thinks. See, it reads your code from top to bottom, one line at a time. So imagine it's inside class A, and it sees the line friend void add A, B. It understands A, but then it hits B and just stops. It says, whoa, what's a B? I haven't seen a class called B yet. And boom, you get a compiler. A forward declaration, just putting class B at the top of the file, is like a little heads up. It's a promise to the compiler. You're saying, hey, don't worry, a class named B is coming. I'll give you the details later. Just trust me that it exists for now. And the compiler says, okay, cool, and keeps going.
All right, enough theory. The best way to really get this is to see it in action. So let's walk through our first example, using a friend function to add up the private data from two completely different objects.
Okay, let's break down the code. Right at the top, you see it. Class B. That's our crucial forward declaration. Then, inside class A, we declare our friend void add A, B, and we do the exact same thing inside class B. This is how we make the add function a trusted friend of both. Finally, we actually define the function itself. And look, it takes an object of A and an object of B, and then it just reaches right in and does obj1.data plus obj2.data. No problem at all.
And there's the proof. The program runs, we enter the numbers 4 and 5, and it stores them in the private data members. Then our friend function add does its thing, reaches into both objects, grabs the values, and prints the result. Summation equals 9. It works perfectly.
So reading data is one thing. That's pretty cool. But what about changing it? This is where friend functions really show their muscle. Let's look at a more powerful example where we actually swap the private data between two objects. The setup looks pretty similar, right? We have the friend declaration in both classes, but look very closely at the function signature. Void swapping A and object 1, B and object 2. See those ampersands? They are absolutely everything here. They mean we're passing the objects by reference. If we didn't do that, C++ would just make copies of our objects. We could swap the data and the copies all we want, but the original objects back in our main function would be untouched. By passing a reference, we're giving the function a direct phone line to the real thing, allowing it to make permanent changes. The function then just runs a classic swap, directly messing with the private data A and data B, and the output here is just undeniable proof. We put in 34 and 80. Before the swap, class A has 34, class B has 80. Then we call our friend function, and after the swap, class A has 80 and class B has 34. The values have been exchanged. That's a direct modification of private data, all thanks to our friend function.
So we've seen just how powerful this is. It lets us do some really tricky things that would be a huge pain otherwise, but that power comes at a price. It literally breaks one of the core rules of object-oriented programming. So we have to ask the question, is this a clever tool, or is it a dangerous design flaw?
This really lays it all out. The advantages are clear. You get access where you normally couldn't, you can share functions between classes, and it can make some operations more efficient. But then there are the downsides. And the big one, the one everyone talks about, is that it exposes private class information. It weakens encapsulation. It's a trade-off, really. You're giving up some of that protective shielding in exchange for more flexibility.
And that really brings us to the heart of it. The friend function is a feature that was designed from the ground up to break the rules for a very specific, practical reason. It chooses operational flexibility over data hiding purity. So, what do you think? Is it a clever and necessary tool for solving tough problems, or is it a dangerous loophole that good programmers should stay away from? The real answer, like with so many things in programming, is that it all depends on how wisely you decide to use it.